Hi, I'm Quinn, and today we're unpacking quantum computing, one concept at a time. A classical computer is built on bits, little switches that are either off or on, 0 or 1. Even if you don't know the value, it still is a definite value. So what makes a computer quantum? It's not, it's fast. It's not, it tries everything at once. The honest answer is, a quantum computer stores information in quantum states and manipulates that information using the rules of quantum physics, especially amplitudes, phase, interference, and entanglement. Let's start with the most important distinction: probabilities versus amplitudes. In classical computing, when we say something is random, we use probabilities, non-negative numbers that add to 1. If something is 50-50, that's basically the end of the story. In quantum computing, the numbers under the hood are amplitudes, and amplitudes can be complex numbers. That means they don't just have a size, they have a kind of direction, a phase. When you measure, you only see probabilities, because the probability is the magnitude squared of the amplitude. But before measurement, the phase is real, and it matters, because phases can make amplitudes combine in two ways. They can reinforce or cancel. And that leads to the next ingredient, the computation model. A quantum program is usually described as a circuit. Prepare some qubits, apply a sequence of reversible operations called unitary gates measure, and read out classical bits. That unitary to measurement structure is the signature. The middle part, the unitary gates, is where the quantum behavior happens. Now here's the key. Quantum algorithms are not just about creating superpositions. If you create a superposition and measure immediately, you mostly get randomness. Quantum algorithms become interesting when they do this: create superpositions, apply phase changes in a structured way, recombine paths, so interference makes wrong answers, cancel and right answers add up. A tiny demo is the Hadamard gate. Start indefinite 0. Apply Hadamard. You get an equal blend of 0 and 1. Measure now and it's 50-50. But apply Hadamard again, without measuring in between, and you get back to definite 0. That's interference. The second Hadamard isn't rolling the dice again. It's recombining amplitudes, so that one outcome is reinforced and the other is cancelled. So if you want one sentence, a computer is quantum if it can control phase and interference in a multi-qubit system. Which brings us to the heavyweight feature, entanglement. Entanglement is what happens when the state of multiple qubits can't be described as separate states for each qubit. A famous example is a Bell pair. 0, 0 plus 1, 1, balanced. When you measure, you get correlated results in a way you can't reproduce just by pretending each qubit had its own independent hidden value. Entanglement is a core resource in many quantum protocols and is widely discussed as a defining quantum feature. At this point, you might be thinking, wait, if n qubits represent a gigantic state with 2 to the n amplitudes, doesn't that automatically mean exponential power? Not automatically, because measurement is a bottleneck. You still only get in classical bits out per run. The art is designing gates, so the final measurement is biased toward the answers you want. That's why the simplistic line, quantum tries all answers at once, misses the point. It's not about having many possibilities. It's about shaping interference among them. Finally, there's the practical reality. Quantum systems are fragile. Noise, decoherence, and imperfect gates constantly push the state off course. That's why scalable quantum computing is tied to quantum error correction, encoding one reliable logical qubit into many physical qubits, so errors can be detected and corrected as you compute. So let's summarize. A computer is quantum if it uses qubits, states with amplitudes and phase, applies reversible quantum evolution with gates, uses interference and entanglement as computational resources, and only then measures to get classical results. That's the recipe. That's all for today. Take care.